Hi everyone, Mr. Boltri here bringing you video 3.6. We're going to talk about Newton's third law. So first, let's do a summary of the force probe lab that we ran in class. So we had three different stations, and in each of the station, we sort of had two force probes, and then we pushed or pulled the two force probes into each other. So we pushed the force probe into the stationary force probe, we pulled two force probes against each other, and then we had two cars, and then we crashed them into each other. And the biggest finding that we found from the lab is that no matter how we did it, no matter which one was stationary, which one was moving, which one was heavy, which one was light, which one was fast, which one was slow, which one was pulling hard, which one was pulling soft, the force probes always had sort of symmetrical, identical readings. We pulled one, the other force probe gave us a reading. We pulled the other, vice versa. So the graphs were always symmetrical, which means that they had the same force, the same magnitude of the force, but in opposite directions. And this probably reminds you of, so the first question that we should ask ourselves is, how in the world can this even be true? And the answer is a little bit disappointing, but it's kind of just the way that things work. Is that we've observed this over and over and over. We've observed that this is just the way forces work. This must kind of be a rule of the universe that we are observing. So just kind of the forces seem to exist this way. We can make the statement that anytime, we've sort of never noticed an exception to this. Anytime one object exerts a force on another object, it gets that same force exerted back on it and vice versa. So forces just seem to exist in this way, which probably reminds you of Newton's third law, which you've probably heard phrased as every action is an equal and opposite reaction. And that's a really short and catchy phrase, which is good to remember, but I also want to sort of improve on that phrase. Because this is a really good way to teach it to middle schoolers. It's very simple, very easy to remember, but it loses some of the nuance that we really need to focus in on that nuance. So it's not bad to remember that, but you also need to remember the way that it is, we can improve on it. So what I'm going to do now, and if you want to write it down, that's fine. Every action is an equal and opposite reaction. It's not like awful. It's not wrong. It just, some parts of it are unclear. So I'm going to go through step by step and improve it one step at a time. So you can just sort of be along for the ride. And then at the very end of the video, you can write down kind of the improved version of Newton's third law. And you're going to think, oh my gosh, it's totally not necessary to do all these improvements when you can just remember every action has an equal and opposite reaction. But the reason that I'm going to take you through each of these improvements is because I've noticed over the years, and there's been studies of lots of physics students, and this phrase actually confuses some people about what's going on. So I'm going to try to remove that confusion by maybe over clarifying what the law needs to be. So my first issue with this law is every action. When I think about actions, I think about like singing and dancing and being in a play and playing football, and that's not what Newton's third law is talking about. Newton's third law is really talking about forces. So we can take it one step and say every action force is an equal and opposite reaction force. So it's already a little bit better because now we're talking about forces, which is good, but we can continue to improve it. When we say equal and opposite, what is equal and what is opposite about these forces? Well, specifically, we can say that they are equal in magnitude and opposite in direction, which we can see by the symmetrical graphs. One is positive, one is negative. That's opposite in direction, but they were always equal in magnitude. So every action force has a reaction force has equal in magnitude and opposite in direction. Okay, it's already improved because now it's more clear. It's clear that we're talking about forces, and it's clear what is equal and opposite. But my kind of final issue with this is when we talk about reactions. Well, I don't know. When I'm walking into a room, let's say I'm walking into a room and there's someone in there to scare me. They're going to jump out. And then as a reaction, I'm going to be like, ah, that was scary. And the weird thing about that is it's sort of one thing happens and then another thing happens. And that's not the way Newton's third law works. It's not one force happens and then another force happens. They happen at the exact same time. They come together. They are never, that you can never have one force without the other force. So we say that those two forces are paired together. It's not action over here and reaction over here. Is they are just a pair. And they always stick together and they come together and they happen at the same time. So this is kind of my big improvement is forces always come in pairs. That's just Newton's third law. We could stop by saying it there. Forces always come in pairs. And so then everything else is just more clarification about those forced pairs. So force pairs are equal in magnitude, they are opposite in direction, they occur simultaneously. But the most important thing here is that forces come in interaction force pairs that are inseparable. You cannot have one force without its force pair. It never happens, or we've never seen it happen, a force all by itself. And the reason is that's just the way forces work. And so you can really easily identify a Newton's third law interaction force pair by looking for if there's a force by object A on object B, let's say by Mr. Boltri on the table, objects A and B, then that pairs with the force by the table on Mr. Boltri. By A on B pairs with by B on A. Those two forces always are equal in magnitude. They are always opposite in direction, and they always occur simultaneously. So this is probably worth writing down as a version of Newton's third law. So let's do an example. We have two cars, let's call them A and B, just so that it matches our example pretty well. And they're going to crash into each other. Let's say A is moving fast and B is stationary. Let's say A is heavy and B is light. We know that when they crash into each other, the heavy, fast A car is going to slam into the car B and send car B flying, and the car A is barely going to even slow down. And so then why is that true? Because if the force, so let's look at the force diagram. So A is a lot heavier than B, it has more force gravity, and in the vertical direction, the forces are balanced because it has a constant velocity in the vertical direction, and A is moving with a constant velocity towards B, which is stationary. So in the horizontal direction, they also have a balanced forces. And then when they collide into each other, the A applies a force on B, and then at the same time, when this happens, this also happens. A applies a force on B, B applies that same force back onto A. So I can use the equality marks to show that it's the same force applied back onto A. But so then the question becomes, why is it true that B just sort of flies off and A barely even slows down? And that's true because equal force, the force on those two cars is equal. But that does not mean that the consequences to those forces are unequal. We remember from the bowling ball lab that if an object has a different mass and you subject it to the same force, it acts differently. And object A was moving fast and object B was moving slow. So then when they both experience a change in velocity, that's going to look different for the two different cars. And then not in this circumstance, but in other circumstances, let's say I go up and push against the wall. Well, why do I move and the wall doesn't move? And that's because the wall, A, has more mass, but also B has other forces acting on it, not just my push. So equal force does not necessarily mean equal consequences because objects that have different mass respond to the same force in a different way. Objects that have different velocities show a change in velocity coming from an unbalanced force in a different way, and the objects may have other forces acting on it. So equal force does not mean equal consequence to those forces. So another way to say that is just because the same force is applied by A on B as by B on A does not mean that they are going to respond to those forces the same. But it is still true that the force on those two is the same, is identical. So here's a very common example that I wanted to show you of something that is not Newton's third law that people often think is Newton's third law. So we have the action force down of the book pushing on the table and the reaction force up of the table pushing on the book. So a lot of people look at this force diagram and say the force gravity down and the force normal up, they are equal in magnitude, they are opposite in direction, therefore the forces have to be Newton's third law interaction force pairs, equal magnitude, opposite in direction. But they do not meet a very important rule by B on A by A on B. The force by the table on the book pairs with the force by the book on the table, not the force by the earth on the book. So this is not a Newton's third law interaction force pair because it does not follow the rule by A on B by B on A. And it's really important to know that we can never see a Newton's third law interaction force pair if we look at just one object, because these are going to be all the forces on the book on the book. We're never going to see any of the forces by the book. In order to see an Newton's third law interaction force pair, we are going to have to look at a force diagram for the book to see the forces on the book, and then a force diagram for the table to see the forces by the book. Because in order to see the force Newton's third law interaction force pair, we have to see by table on book, and then by table on book by book on table. That's the Newton's third law interaction force pair. So this is worth writing down. Make sure this is in your lab notebook because this is really important. Obviously, every action is an equal and opposite reaction is snappier and easier to remember. The snappy, easy thing to remember that I want you to learn from this is forces always come in pairs. Forces always come in pairs. It's only 5 words, you can remember it. Forces always come in pairs. And then we can talk a lot about those pairs and what they do and what they mean. For example, they are equal in magnitude, they are opposite in direction, they occur simultaneously by A on B pairs with by B on A, and equal force does not always mean equal consequence. That is all important information that surrounds the big idea is forces always come in pairs. In our next class, we're going to do some practice problems about Newton's third law. But until then, let me know if you do have any questions. But right now, this is Mr. Boltri wrapping up video 3.6 on Newton's third law, and go Bears.